I hope so. Chat, are we live? Are we live?
I'm refreshing the page to see what I see.
Are you on the YouTube thing too? Let me know if it's working. Is it showing
Don't
up?
see anything yet. I don't know how long the delay would be.
So we got 4 watching, so it should be showing up.
Shows us 16 on my page.
Little picture though.
Yeah, it's still your picture and it says waiting.
Somebody said sounds good. Somebody says they hear something. I probably started a new stream somewhere. God damn it. Yeah, probably because of the glitch. It just started a new stream. Just refresh the page, see if it goes up on a different link on my YouTube channel somewhere. Technical difficulties suck. Videos. Live. Yeah, we're live on the wrong settings, but it's all right. I added that. Change the settings real quick. See. Back. Edit. B.
All right. So
you see it now?
Yeah, I do. Just send in the new link to the old channel, the old video.
Yeah, that was my bad. Technical difficulties. Shit happens.
Yeah, no worries. So we're live now.
Yep. They say no audio from you. Can you hear me now?
Probably I was muted, but I'm unmuted now.
Okay. Can you hear him now?
Yeah,
okay,
sounds like it's working now.
All right, cool. So Joshua, thanks for coming on and having a conversation with me. I really appreciate you taking the time to discuss flat Earth with me. Would you mind telling us a little bit about yourself before we get started?
Sure. So that's actually the very beginning of my introduction here. So I'm a product of homeschooling. So moving into the flat earth world, I was really used to the ridicule already. So I've got some thick skin and I really love semantic debates and conversations. I have a science degree in computer networking. I've been a field engineer in telecommunications most of my life. I began teaching back in 2010, primarily engineering. But now I'm teaching political science, debate, and public speaking, and that's kind of how I got sucked into this whole flat Earth conversation.
Cool. So you got a presentation. Like I obviously think the world is not flat, and you think it is. So, would you mind? Let's tell me what your position is.
So I'll talk about kind of like my progression down this over the past the 2 years of why I'm interested in the study of the shape of the Earth or geodesia. About 2 years ago, I started really looking into the Apollo moon landings. And I think from what I've heard on modern day debate, you do think that they've happened. So I'm starting from a point where I don't at all. And that was about a year of study, and that really kind of wrecked my world, to be honest. I was quite the gung ho little GOP space dreamer, like everything I should be. Wanted to be in the military, but didn't make it. And just I was very nationalistic in mind, and to find out that the American government could lie like that, it kind of blew my mind. And then in 2019, a debate student of mine asked me if the world was flat, and I was like, of course it's not flat. But I didn't really know how to debate or argue it because astronomy is not anything I've studied before. So I was like, give me a week and we'll talk about it later. But it's definitely not flat. And then July of 2020, I've sent this email to you saying I want to have a conversation about it and see if I've just lost my mind or not. And so I labeled this, because I'm a teacher, so that's why I've got this presentation, and I'm very formalized in this. I labeled this my sincere study of geodesy, or the study of the shape of the Earth. And I want to talk about why it's sincere, what's different from mine. So since I began this like I was going to teach a student how to win a debate, it needed to be something that everyone could understand and observe. So I began the study of accurate and pragmatic geometry of the shape of the Earth, and I dropped all presumptions and all hypotheses. I just thought that everything needed verification. If they could lie about the moon, what couldn't they lie about? That was my whole life at the time, right? So predictable observed phenomena became my only laws. And so I think you and I were probably going to agree right in the middle of this, of what a difference between a scientific law is and what a scientific theory is. A law describes what phenomena will happen, and a theory is us trying to explain why that phenomena occurs. And then our sweet spot, I've heard you say a couple times, science doesn't prove anything, and I agree with that so much. But that sweet spot is we can make these repeated predictions with experiments that verify our results. And so that's what I just started looking for in this area. And so what are the phenomena that everybody talks about when it comes to the shape of the Earth? It's the sun sets and rises predictable times each year. Seasons change, and it's predictable, and our sun appears to move above us depending on where we are. I live in the equator now. I live in Saigon, Vietnam. So it's always a 12-hour day for me, but where the sun is on the sky switches. So it's pretty cool growing up near Washington, D.C., and then coming around the world, not across the globe, but around the world, has been a wild experience. I have been on a plane. I have circumnavigated the world very many times, east to west. That's definitely doable. So solar and lunar eclipses, I realize they're just predictable on what's called a Saros cycle, which is about every 18 years, 11 days, and 8 hours. And if you stand and you see one, you wait 18 years, 11 days, and 8 hours, and you'll see another one. The fixed stars and the sun traverse in complete circles in our sky every 24 hours. The moon traverses a little bit slower than the sun, but they line back up every 28 days or so. And then here are all the theories that I've been taught since I was a kid. You know all these. The Earth rotates on its axis 15 degrees. It orbits once around the Earth per sun on a 24.4, 66.6 degree tilt. Earth's obstruction causes a lunar eclipse, and the moon obstruction causes a solar eclipse. The fixed stars are the same as the sun, but they're super far away. The moon is 400 times closer than the sun, and the sun is 400 times bigger. That's why they always line up perfect for us. So the scientific method, I've heard you quoted a million times. This is more for any of our watchers. This is all about what I was trying to do. I was observing phenomena. I was questioning, why does it happen? Making my guess, and then trying to design an experiment, predict what will happen, then do my experiment. And that's all I was doing. So my first thought was, well, if we orbit the sun, we obviously are a globe Earth, a flat Earth going through a sun. It makes no sense in any conceivable motion. And first thing that we began with is what I was taught since high school physics, which is big G, right? The gravitational constant. And I really had no idea where anyone had gotten that before. I just knew it was gravity. And it's an unobservable and it's unverifiable, as I learned, right? And if you can challenge this and you can change my thinking on this, I'm really excited to learn how. But from everything that I've been reading for the past 2 years, it's a mathematical law for sure, because that's how math works. You set a constant and it's constant, but it's not a scientific law. And an object does accelerate downwards at 9.86 meters per second squared. That's a law. Like, that happens. I'm not crazy. I know that happens. So Newtonian gravity is very different than what we talk about as gravity now. But Newtonian gravity, you would think if you dropped a penny next to a mountain, the penny would kind of fall in an arc. In Newtonian gravity, the way that I read the math anyway. Obviously, with Einstein changing everything, it's no longer just objects of mass sending waves through the ether. It's more about a ripple. And so we've got Henry Cavendish, and I call him the Great Balls of Liar. I'm a big Jerry Lee Lewis fan, so I thought this was funny, even if no one else does. And you're really familiar with the Cavendish experiment, I'm sure. Flat earthers have torn this apart to shreds. I know you've heard all of this already. He put these big, giant balls next to these little tiny balls, hung them on a string, and tried to get the balls to go back and forth. And was it tension on the string that made them rotate? I don't really know. Students do this experiment over and over and over with ball bearings and bowling balls, and they all get different numbers by wild margins. And they're like, oh, well, you didn't account for this, and you didn't account for this, and you didn't account for this, and you didn't account for this. But it works, trust me. Just fix your number to G and then move on. You verified it. So I just deny, I deny that this experiment proves anything because it wasn't predictable. There's not a prediction you can make and you can do it. Unless you're just going to say the balls can swing, but then I'm going to say it's tension of the rope. Like, that's crazy to me. So I assumed that I'm going to go all a posteriori arguments. I want observed phenomena, like I'm doing this study from something I can see. And I'll, if you want to interrupt anytime, this is really long, so just go.
Oh, sure. Yeah, there was a couple things I've already taken notes on. So the first thing would be theory. So a theory in science is higher than a law. A law is just a single part of a theory. So the word there should be hypothesis. Hypothesis is the explaining the phenomenon, and then after it's confirmed with testable predictions, then it becomes a theory. So a theory is actually like it should be a bigger circle around the two.
That makes sense. I think I would totally agree with that.
And then you said something about a penny. If you drop it from a mountain, it'll fall to the side. Because my understanding,
if you look at, go ahead.
My understanding of Newtonian and Einsteinian gravity is the penny's going to fall down the entire time. It's going to hit the rocks wherever you drop it. I don't know why it would fall.
Definitely, it's going to fall down. My argument would be, if I had a mountain of significant density, it would still certainly go down, but it would go down at an arc. The mountain of the gravity would still be affecting the penny, which is contrary to all observation we make. The only gravitation we can observe on Earth is directly downwards. We can't create anything of significant mass or density that pulls away from the Earth.
Right, because you'd have to be bigger than the Earth.
Not in my understanding of Newtonian gravity. Why would it have to be bigger? Because why would there be a baryton center if it had to be bigger? The Earth still attracts on the sun with its gravity, even though it's not bigger than the sun. All mass would be sending these waves of aether out, according to Newtonian's theory, or Newton's theory, excuse me.
Newton's theory didn't have anything to do with the aether, but it's not about the gravity of the mountain definitely affects the penny, but it's just not enough to do anything. It's like if I tried to blow on my TV, it's not going to fall over because it's just not enough force. In order to have enough force to actually guide the penny to fall in like an angle, I don't know, like if you drop it next to the mountain, like away from the mountain, you're saying? So yeah.
The idea would be that
if you're like on top of the mountain and you drop it, it's just going to go straight into the mountain. So
sure.
You're like
it would be like, let's say we had a flat cliff wall and we were dropping it down that cliff wall. That would be my thought, the entire weight of the mountain. And I did this one a really long time ago, and it's not in my presentation, but Newton's mathematics behind his gravity was rather simple. It wasn't very hard to sit down and do that and prove it wrong. Excuse me, let me mute that. Prove that wrong just based on the fact that we can make things heavy enough that we should have been able to observe the force.
I don't think so. I haven't seen, my understanding of Newtonian mechanics is that's not how it works. Like I did pretty well in education, so I'm pretty familiar with Newtonian mechanics, and it doesn't really affect. There's no way we could have made a big enough thing to affect gravity in that way, because the gravity is proportional to the size and mass of the object. So in order to have enough gravitational force to tilt a penny like even like 1 degree off of from dropping it is going to
my argument would be measurably. I haven't done the math with the penny, to be honest.
Well, yeah, so
the argument would be we should be able to build something where we could measure a gravitational pull, and we cannot. In Newtonian's theory of gravity, like I said, his math was not.
I'm pretty
difficult.
familiar with the math. The math says that in order to make something sufficiently to affect the gravitational force, it's going to have to be larger than the center of mass of the Earth to be able to do that. So it's like
that would be just to pull it completely to it. That would be to override Earth's gravity. Think about the games that involve gravity. They're always using Newtonian gravity in theory. Like I can't remember what it was called. There was one. I'm drawing a blank, but the video games where you would make these arcs around the planets, but then other planets and stars would pull you as well. In Newton's theory, you would have these constant waves of gravity pulling you on like this yo-yo game. I can do a follow-up on that where I've done the math to verify that claim, but I don't find it super important because Einstein kind of dismissed everything that Newton said anyway.
He didn't dismiss it. So Newtonian gravity is still
gravity.
correct. It's just less. Correct. It's not accurate to the same level of accuracy. So it's still correct. Like Newton didn't get it wrong. He just had a lower level of accuracy than Einstein.
But his math is. I mean, how would the Apollo moon landings work with Newton's math instead of Einstein's?
Just less accurately. So it's like if I use a musket from the 1900s, no, it's not wrong. It's just less accurate. So if I use a musket from the 1900s, like it's still going to make the bullet go in the correct direction. It's just not going to be as accurate as if I use a modern day rifle. They're both still going to go in the right direction. They're both still workable models. There's just one is just more accurate than the other. So they still work. They both still work. They're just one is more accurate than the other.
So it makes me think of Isaac Asimov's The Relativity of Wrong. Like, I mean, we're saying the same thing. We're just arguing about terminology. In my opinion, it's wrong. You're saying, well, I mean, think about it. Like, even in that paper that Isaac Asimov wrote about the relativity of wrong, his example was the flat Earth or the spherical Earth, and he's like, the flat Earth isn't wrong because it only occurs at 0.00126 miles per mile. It's not wrong. It's just a little bit wrong. We know it's kind of wrong. We know it's relatively wrong, and so I mean, Newton was not right. His math doesn't make accurate predictions.
Well, it does. It makes lots and lots of accurate predictions.
Well, which ones?
Like
what astronomical predictions did Newton make?
Like if I throw a baseball and I use Newton's equations, I can get the accuracy of the baseball pretty close, like within inches. So it's really good. It's just not within micrometers or microns.
Sure, but he was talking about giant objects of mass. So if he's going to make predictions about gravity, he should be able to predict where the planets are going to be and the sun that's going to be and the moon's going to be and stuff like that.
Yeah, and he did. So he got all of those right except one.
No, he didn't.
No, he did. He did. So that part he got right.
Can you verify any prediction he made about any planets?
Yes, you can use his equations to calculate the motion and speed of the planets and where they would be given the current model.
That isn't
right.
That isn't a prediction, though, right? Because he already knew where they would be. So he didn't make a prediction. He knew where they were going to be, and he made a mathematical formula that continued to predict it based on what he already knew. He reverse engineered that, right?
No, he didn't look at the planets.
He did know where the planets would be. We've known that for like 3,000 years. The astrolabe has been able to predict the location of the planets since 500 BC, right? The Mayans did it even before that. The Chinese did it before that. How can you say no on that one?
Because we didn't even know about most of the planets back then. Like, we can't actually see them from the system. Like,
okay, so thing called minus Uranus and Pluto.
Well, no. Like, there was until like the 1700s, there are these two stars, the morning star and the evening star, and we thought they were two different things. And then we learned out, they're actually the same thing. They're a planet that just show up at different times during the day. So we didn't have...
What astronomer thought that? Chinese astronomers sure as hell didn't.
Yeah, they did. Like that one, it's pretty common.
Can you verify that one?
Yep.
Definitely not. On the Chinese astrolabes that I've seen in pagodas here in Vietnam, Venus is labeled the Diamond Wanderer, I think, the same name that it's had since antiquity, and it's not twice. And it's 1,600 years old, I think.
Right, because they didn't label the same thing twice. They labeled them two different things and got it wrong. One of them doesn't exist.
No, they only labeled Venus what they call it, and that is it. It didn't happen twice. That's just not true. It's all right. I would love it if you could give me a source on that, because I would change my thinking.
Just morning star and evening star. It's a fairly common example.
I'm not saying no astronomers ever made that mistake, but I'm saying there are very many who didn't.
It's sure it's possible, but there's lots of things about cosmology everyone got wrong. None of them got it right. They all got it wrong. And so until we actually learned in the future, like Newton got it more right than anybody else.
Cosmology or astronomy? Because the
Both.
predictions of where they no, well, they're totally different. One's a philosophical study and one's a mathematical study.
No,
Oh,
they're both studies.
that's
Like neither one of them is math. Math describes things in reality. So both cosmology and astronomy are looking at the bodies in the sky, and then they use math to describe those bodies. Neither of them are abstract math. They're all
so
just
I subscribe to a Western classical theory of education that was created by Plato in the Platonic Academy that outlines the four numbers in the quadrivium. You study math and abstract, and then you study math in time, which is music, and then you study math in space, which is geometry, and then you study math in time and space at the same time, which is astronomy. That's where our stars will be when they will be. And then only after you've studied the 7 subjects of the classical education called the trivium and the quadrivium may you begin to study philosophical things like cosmology. They're totally different. And if we're going to study the shape of the Earth,
so that has nothing to do with they're completely separate fields.
That's to say that's not how academics works is not how academics works.
No, it quite is. Like
academia invites different philosophies of learning and different authorities of education.
No.
The Platonic one is certainly valid.
The order of the way you learn it does not matter at all. Like scientists don't care what philosophers think. Scientists do not care what the abstract mathematicians think. Scientists do science. They do.
May I read this quote now from I think it's Time by George F.R. Ellis, written in the Scientific American in 1995. People need to be aware that there is a range of models that it could explain the observation, Ellis argues. For instance, I can construct you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observation. Ellis has even published a paper on this. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring out into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that.
Yeah, he's wrong.
Counter, Professor.
Oh, he's wrong.
Who says that?
Everyone says that. So
please, sources, names, papers.
Everyone, just pick a scientific paper. So all the models in science.
I want you. No. I want you to do that.
I'm doing it right now. I'm doing it right now. So everything in science is based on novel testable predictions. The philosophy just doesn't matter. No one cares. You can make up whatever philosophy you want. If it makes testable predictions, it wins. So we're not making decisions based on philosophical grounds at all. It's all based on testable predictions, which is why in current cosmology, no one accepts any of the current models because none of them make testable predictions. They can all explain the data. No one cares because none of them make testable predictions. The way science progresses is whichever one makes the testable predictions that can be demonstrated true in reality, that's the one we go with. So
sure, but doesn't it bother you that heliocentrism can't make any testable predictions?
It does. It makes the prediction that the Earth goes around the sun, not the other way around.
Yeah, but you can't prove that.
We can literally see it. That's a way to prove it.
You can literally see the sun go over your head, Tom.
Yeah. We can also go into space and literally see the Earth go around the sun.
I think that's an entirely different debate. So I did ask you at the beginning, because I already don't believe in the moon and the ISS, that we can't really use that as criteria.
Well, no, you
I would
said,
love to have.
You're right. That's not part. I'm not trying to make that a debate point. What I'm saying is, you said
yeah,
that
but I don't believe that we've done that.
Right, I agree. I agree. You don't believe that. So that's not the point I'm making. You said heliocentrism doesn't make testable predictions. It does make testable predictions. It says the Earth goes around the sun. The sun is a giant ball.
On your assumption that we've been to the moon, it makes testable predictions.
This is not. A testable prediction is when you start with a hypothesis, assume it's true, and then predict what the consequences are going to be. You don't test them. That's not the point.
When did you do that?
No. Testing is not a part of the testable predictions. You can make a testable prediction without actually testing it. Like I can make a testable prediction.
Fair enough, but
so the way testable predictions work is that you make a prediction based off of a model and which can be tested. It doesn't need to be tested.
I've made several in my experience.
Right. So heliocentrism does make testable predictions. It predicts things that can be tested.
I guess I see your point. It does make testable predictions. Right. I say we've never tested any of them.
Right. That's perfectly fine.
Good point. I agree. If we went out to the moon, that would be testing our prediction. You're totally right. I just think we haven't done that. I understand your point. I'm sorry.
Okay.
I totally get what you're saying now. So I think you understand this. You obviously stand in opposite of him either, so that slide's not even important. And you probably think Dr. Kaku, professor, is wrong as well. This is a pretty viral clip back from 9, 10 years ago, so I'm sure you've seen it. But he says, in science, we say you make observations and you have a theory, and it's a very tedious process. Wrong. No one I know in my field uses the so-called scientific method. This is the interview he did with C-SPAN for books he's written. He's a theoretical physicist. I think you've already said you stand on the same ground with some of the cosmology there, where they just make things we'll never be able to test and predict, and it's a lot of pseudoscience. So I think I'm preaching to the choir there. This is from Ptolemy, who was one of the first astronomers that ever, from my deep dive, ever really believed that the Earth was a sphere. So I've been reading him and studying him a lot, and he's got the same thing that I'm talking about with the difference of philosophy, but I don't think I need to read this quote. I think it's redundant.
Well, just a quick point. The Michio Kaku, he's talking about a specific kind of scientific method. Like, they all use the general scientific method. They just don't use the thing that's been labeled and you find pictures of it on the internet. That's not what the scientific method actually is. The scientific method is make predictions and test stuff. It's not just there's the thing.
I think his point is that they don't test stuff.
They definitely
I think
test
his
stuff.
point is, no, he doesn't. He just writes books, man. He doesn't test nothing. He just
I don't know specifically
thinks.
what Michio Kaku's position is, but I do know physicists definitely test stuff.
He's a professor in the physics department.
No. I know what he's a professor. So but I don't know what I don't know what his specific field is and whether or not he tests things. So, for example, he could be a particle physicist in which he does test things. Like, he could actually go to the Large Hadron Collider and test things. He may do that. I don't know. I don't know enough about his job. So, but there are physicists that do that. They do build these machines to test things. Like the LIGO detector, that is a detector. They do experiments. The Large Hadron Collider, that is a detector. They do experiments. The Hubble telescope, that is a detector. They do experiments. They do experiments. Not all fields of physics. Like, there's theoretical physics that doesn't do any predictions. It's just theoretical. Sure. But they're designed to make predictions. And which is why people don't accept them until they make the predictions.
Sure, I don't disagree with that. I think you said that.
So Michio Kaku wasn't disagreeing with that either. He's just saying that.
I don't think he was okay. Either. He was talking about the people that work with him, and he was saying we don't test shit.
Okay, that's fine. Sure.
Is it? And he's talking about. So these are some things that, like, these are what you're saying. We have tested it. We can test that the Earth is a globe. How have we done that? These are all at least the things that all popped into my mind when I very first began this study. I thought that all star predictions were done based on a heliocentric model. I thought that eclipse predictions were done based on the globe model. I thought that the moon landing was real and the ISS was real. I thought there were pictures of the Earth, and I thought satellites were just assumed. So I'm going to make some positive claims about all these 6 things so that we've got some talking points. No computer software in existence can predict fixed star locations based on a heliocentric universe. That really blew my mind when I realized that.
What does that mean?
So all computer programs that will track where stars are in the sky, they all assume a geocentric universe. All of them.
No.
All the algorithms based on the star movement and predicting where it's going to be, they're all done on the assumption that the Earth is the center of the universe.
No, they're done on the assumption that we're looking from the Earth. And so in order to know what its location is going to be, you have to look at it from where you're on Earth to where it's going to be. It doesn't tell anything about where the Earth's location is relative to the universe. It's where the star's location is in the sky at night.
That's how computer programs work.
No, that is incorrect. So the computer programs work by saying, here we are on Earth, and we want to know where the star is, so we have to start from where we're standing and look in the correct direction of the star, which means we're starting
maybe like a Flash one on your browser would do that, but if you download one of the higher end ones, what they're going to do is they're going to create what's called a celestial sphere around a globular Earth, and they're going to move this star field around it.
Yes. So if you want to know where the stars are, it's
definitely going to start with this. Was how they'll build this tracking, and they'll zoom in and do perspective.
That's not a geocentric universe. That's a where you are looking from. Where is the star going to be? So if I wanted to say, where is my computer going to be? I have to start from where I'm sitting and then say the computer's that way, and then the camera's that way, and then the phone's that way. This is not a me in the center of the room theory. I'm not saying that I am in the center of the room or the center of the universe because I'm pointing to things and saying they're over there compared to me. I'm saying from my perspective, if I want to know where it is, I have to reference my starting points to get there. That's what all of those models are doing. They're saying from where we're standing, if we want to know where a star is, we have to start from where we're standing and then give a direction. Just like I would say, the camera is there. This does not mean that I'm in the center of the room. It's not how it works. I'm just using me as a starting point. Does that make sense?
Sure, but if they didn't move, you'd have a point. But since they moved for 5,000s of years, how do they move? They move in a perfect orbit around what the computer programs as the Earth, which was my point. So if it was a still image, you'd be right. But since they track it for 5,000 years, that's pretty much what everyone does because they just steal what the Babylonians did.
I have no idea what you're talking about. So if I imagine I'm on a spinning chair and I start to spin on my spinning chair, everything in the room is going to be spinning at exactly the same rate and speed, essentially. And I can say, oh, if I want to know where the camera is, I have to stop and say the camera is going to follow some particular pattern relative to this.
It's not about you on the spinning chair. It's about you making a computer program that will predict where everything in your room is based on.
So if I wanted to make a computer program to describe where the camera is going to be based on my spinning, what I need to do is I need to calculate the speed of my spinning and then say, here's the location of the camera relative where I am now. And then apply the program and say, if I'm spinning at this rate for this long, then the camera will be here. So that does not predict that I'm in the center of the room. Nowhere in that equation does it say I'm at the center of the room.
It's just a computer program. It doesn't make predictions.
Yes, computer programs make predictions all the time. So, but again,
this one does not. I mean, you could say that the GUI makes a prediction when you say, let me go to 2040 and see where the stars are. Sure, I get your point. Yeah. But what the computer program does is exactly what the programmer told it, which said, move these stars around the Earth.
Yeah.
Like it is not a scientist. It's not making predictions in the sense that we mean it. The graphical user interface can make predictions based on the algorithm that the developer made. Sure, not my argument. But the stars do move in these computer programs, and they do move in orbits around the Earth. Yes. I get that you already know that, and you're saying that's obvious, but it was still something that I didn't know. I assumed we could make a computer program that would have stars moving as they legitimately are, and we could, from our position of Earth in a heliocentric universe, observe them. But we can't.
What are you talking about? So if I'm spinning on a chair, the camera's going to appear to be moving to me, even though it's completely stationary. The camera isn't actually moving; it's just sitting in one spot. But if I'm spinning,
wouldn't we put your chair on a train and then spin on the chair, and then your chair's going around a train?
You can move it in lots of ways.
And then you doesn't put that train on a boat, and then that boat's going like. It's not just your chair.
You can do that. You can do it in different ways. But the camera's still going to be sitting there, and I'm going to be the one moving, and that's perfectly fine. Like there's no problem there. That's not me being the center of the universe. That's just me trying to figure out where the camera's going to be relative to where I am. So none of these models actually say there's a geocentric universe. They're just saying we start on Earth when we look at stuff, and so when we want to know where it is, we need to know where it is in reference to where we are.
If the computer was sentient and you asked the program whether it thought the universe was geocentric, it would reply yes. But
no,
it's not saying anything about our universe. It's making a star chart. And how it begins with that star chart is something called a celestial sphere, which assumes a geocentric universe and a perfect rotation around that sphere.
I'm not sure what you're not getting here. So it doesn't assume anything about the shape of the universe. It doesn't care. All it's saying is we start here.
Okay, you're right. I guess it doesn't assume, it just builds the universe.
No, it doesn't build the universe. It says we start here. It builds like what we're looking at. It's like if I look at things through my eyes, that doesn't assume a me-centric universe. It doesn't assume the universe is revolving around me. It says this is where my vision comes from. This is where I'm looking. The model
sure, but now make a computer program that predicts what you see when you go outside of your house. Like that would impress me.
Sure, that's essentially what it's doing.
But if you just were perfectly still in the middle of your room and all you did was look around it and nothing else happened, then okay, you can build a computer program to predict it.
So all the computer programs are doing is saying what we will see when looking in that direction from Earth. It's not saying the Earth is the center. It's just saying if we stand here on Earth and we look in that way, this is what we're going to see. That's what they're doing.
What the computer program does is it builds all the known stars in our universe that we observe, and it builds them in a perfect sphere. And then it puts another sphere inside that sphere called the celestial sphere. And then when you ask the computer program for a specific point to view, it then rotates the stars around the stationary Earth that you're viewing from and goes to your day and aligns. I mean, I think you understand the programming too. I don't really know what we're arguing about. You're saying that it has to be that way. I'm saying that, sure, but we should be able to make one from the heliocentric point of view as well.
We can. There's one on Google that does that. So I don't understand.
It doesn't.
It does.
Like, that would blow my mind, but I'm sure it does.
It literally does. Like, we have this in video games all the time. We have lots of these. So, but you said this is a
Sure. But they don't. Yeah, you're right. In video games all the time, they do work in heliocentric models, but they can't make accurate predictions about our stars. They're fictional universes.
No, they can. They all do. But if you want to make a prediction of what we're going to see from Earth when we're standing on Earth.
Yeah, sure. Can you name the video game that can make that accurate prediction from a heliocentric universe?
Yeah, Google Maps. Just Google Maps, keep scrolling out and just scroll out all the way.
Yeah, Google Sky it's called when you look at the stars, and that definitely uses a celestial sphere.
Nope. Again, incorrect. So again,
can you give me a paper by one of the developers or
pick
white
Google Scholar, geocentric model?
Why do I have to find your sources all
because
the time?
I don't need the sources here. This is not like I didn't come like if you wanted a list of sources, you need to give it beforehand. So here is the evidence.
Oh, I'll send you an email asking for all these sources. I mean, I just don't believe you. I've already looked for all these, man. I've been on this for 2 years.
That's fine. So again, what you're saying is wrong. We can prove it wrong in 5 seconds. All of the models, when they're predicting...
Do it.
That's what I'm doing right now. Now stop talking. So all of the models, what they're doing, those models are saying what we will see when we are standing on Earth and look in that direction. We're predicting where the stars will be when we are standing on Earth looking in that direction. The stars don't actually move. So if the star is going to be in one specific spot relative to the sun, it's always going to be in that specific spot relative to the sun. There's no movement. The reason we have to predict where the way we're going to move is because the Earth is moving. So if I'm moving around the room and I want to predict where the camera's going to be, when I turn around, I have to predict from where I'm standing. That's why the models use the geocentric kind of a shape, because they're telling you where the stars are going to be relative to where you are looking. There's no geocentric model there. That's where your eyes are model. This is where your eyes are coming from. That's it. There's nothing about that.
No, the computer program renders the location of the stars before you ask for a viewer location, actually.
No, it doesn't. It literally is the viewer location. That is what it is calculating. That is the thing it is calculating.
That would be a very terrible computer program.
No, that's literally.
There probably, like I said, there probably are some Shockwave Flash browser ones, and maybe the Google one does do that.
Every scientific
but all the high-end ones.
Every scientific model does this exact same thing. It's predicting what you're going to see when you look into the sky. That's it. So it's saying your viewer.
But you're saying it doesn't. And I know what the tool is used for. I'm not arguing.
No, I'm saying this is literally what the program.
And you're saying that it uses a geocentric looking shape, but it doesn't.
No.
I know it uses a geocentric model. You know it uses a geocentric model.
No, it does not use a geocentric model. It uses a.
Does it use a heliocentric one?
Yes, it does. What it does is it shows. Can
you show me a white paper by an engineer who developed a single algorithm?
I don't even need to. Every single one of them. So again, I'll explain it again. Okay. The way the star charts work.
No, I want.
I don't care. I don't care. I'm not interested in educating you on science. You can just Google any scientist. They're all going to agree with me on this. So, but I can explain it to you again. I'll have you explain it to you again and prove you wrong again. I don't need a paper to do it. I can do it myself. It's very simple. The models are going to predict what you will see. They are looking from your eyes, saying, what will your eyes see because you're moving? So obviously it's going to be a you-centered picture because it's coming from your eyes. It has to come from your eyes, so it's going to be a you-centric model. It doesn't mean that you're at the center of the universe. It's not a theory of a you-centered universe. It's a theory of what your eyes are going to see. So what is the Earth going to see when it looks out, when you look from the face of the Earth into the sky? That's what it's telling you. It's literally predicting what our subjective perspective is going to look like when we look into the sky. It is not predicting the stars are literally moving. It's not a geocentric model of the universe. It's saying what we will look like when we look into the space. So if I sit here and I rotate the room, it's going to look the exact same as if I rotate on a chair. It doesn't matter if you rotate the room or the chair. It's not saying that I am the center of the universe because I'm rotating the room in the 3D model. That's not what it says. It's just a way to represent what you will see. That's it. So there's no geocentric model there at all in any of them, in any models ever.
Well, this image that's on my screen is from a white paper that says everything you just said was not how they work. But okay, you don't want to prove that to me. I think you're wrong. You think I'm wrong. I think we can move on, right?
That's fine. Yeah, I'm just going to go with all of the scientists who all say I'm right. Every single one of them.
I would just ask for a name, dear Tom.
Pick a scientist.
But moving on.
Neil deGrasse Tyson, Sean Carroll, Michio Kaku, he's going to say I'm right.
Tyson?
Yep.
What? He doesn't know anything about
You said pick a name. I can just pick any scientist name. Carl Sagan.
I wanted a white paper of an engineer who made a program that could predict the stars because I was reading people who made the tools, and you're talking about
pick any one of them, and they're all going to say the same
YouTubes.
Thing.
All right, so let's talk about my man Fred Espenak. Sorry, he's crazy. No one can predict eclipses based on any model, flat Earth or globe Earth, which is hilarious.
What do you mean no one can predict eclipses? We can predict every one of the eclipses with exact accuracy.
We can do that, but not based on any model. I'm going to explain.
How do we predict something without using a model? How do we?
Are you ready?
Go for it.
I'll tell you. All eclipse prediction is completely done 100% based on past observation, which has nothing to do with either scientific theoretical model, the globe Earth, the heliocentric, the geocentric, or the flat Earth. It's just, I see an eclipse there. Wait. Oh, there it is again. Wait. Oh, there it is again. Every 18 years, 11 days, and 8 hours, that's going to happen again. All of NASA's eclipse predictions, all of them are done by this crazy guy right here on my screen, Fred Espenak. Fred Espenak published 5,000 years of eclipse data, did it in one book, just like everything's for 5,000 years because they're all stealing off of the same Babylonian observations. And it's all 100% based on previous observations of Saros cycle. He's a brilliant historian. He is a great anthropologist, but he doesn't really know anything about astronomy. What he did is he went to all these ancient places and gathered all their eclipse writing, recorded the data, and then made predictions on the assumption of the Babylonian Saros cycle.
So pause right there. So yes, people have seen eclipses for lots of time in the past, so you can definitely use the past evidence to predict when they're going to be in the future. If it happens every 18 years.
That's the only way any eclipses has ever been predicted in the history of mankind.
No, that's the way they predicted them 5,000 years ago, and they just got them right. So we haven't predicted a new one. There's not like we're going to predict a new eclipse that's going to be there because of the new model.
Sure.
That's not how it works.
I agree. Like the prediction's been made, so like we can't cheat. But I'm going to show you like one of your
But that's the thing is that we can now predict them with more accuracy with the new models.
No, we can't.
Yeah, we can.
No, we can't.
Yeah, we can get the exact minutes.
All right, so here's my proof. You don't like proof, but I have tons of it. All eclipse calculations, this is nasa.gov/eclipse. All eclipse calculations are done by Fred Espenak, and he assumes full responsibility for their accuracy. All him, just alone. No computer models, no algorithms, no more accuracy.
That's just that website. That's not all of NASA's calculations. It's just that one website.
Okay, prove me. No, you don't like proof. Okay, I've been looking into this for 2 years. Like I've been here. I've done that. Eclipse predictions by Fred Espenak. It's all of it. It really is. Here's more of it. Here's basically just him going into his writings of the Saros cycle. Like I said, they're just on repeat. I mean, you're right that since the predictions have been made, you can't really say that your model figures it out, except for the fact that we have computers that can run simulations. So in theory, you should be able to make a heliocentric universe that can accurately predict eclipses without knowing the Saros cycle beforehand in a computer, but they haven't.
They have.
I would love to see proof on that. I've been looking for 2 years. I would love a single program that can do that. Here's the Great American Eclipse, and here's me using some free software that I can use to try to predict eclipse, just like you say it can be done.
So just to clarify, all of the software is doing is just taking the equations and just making it into a picture. So general relativity, any program that does general relativity is going to get you the result. I can make a program to do it. 5 minutes.
I would love to see that. That'd blow me away.
It's very simple.
Here's me using a free one online that failed demonstrably. So you might say the programmers are shit, but take a look. So you know the Great American Eclipse that happened 3 years ago?
Nope.
You don't know the solar eclipse that happened 3 years ago? That went all through America?
Yeah, where there's a big shadow. That's known as the Great American Eclipse? Sure.
Yeah, if you Google Great American Eclipse, you get it. Okay, the name's dumb, but you know, August 21st, 2017. I'm talking about a real thing that happened. Eclipse began over the Pacific Ocean at 3:46 UTC, and then it moved eastward over America, and then it dipped out somewhere east of Cuba. So here's an image from suntimeanddate.com of how that shadow went, right?
Okay.
And here is solarsystemscope.com. Like I said, I'm using a free one. You're saying you can make a program in 5 minutes that can do this. But here is this, me just going to the same date. This is Vietnam time at the bottom, guys. I'm +7. So this is the same time in UTC.
Well, they can't see it because it says Joshua's other PC is at the bottom.
Ah, I see.
If there was something they were supposed to see.
I want to make sure they see the date right here at the bottom. So I'm going to pull out so that you can see that date. 3 a.m. would be the very end of the eclipse because I have images stacked with animations. So we're going to watch basically the way that America moves. We can see America chilling right here. And we see it goes like this through the duration of the eclipse, right? Sorry, I readjusted my screen in the middle. That's why the animation sounds so smooth. So as they go through here, like boom, we can see that if the sun was casting a shadow on the Earth, it would very obviously start in the Atlantic Ocean and go to the Pacific. But in reality, we saw it do the opposite. So that was one. You're saying you could make one that do in 5 minutes. I would love to see that. That might change me.
Sure, here's one from
like
NASA.
This was a big thing for me.
The testing of general relativity, precise formula, starlight deflection is given. Testing on the NASA for testing general relativity, nasa.gov/testinggeneralrelativity.com, Eclipse 2017. Done. There's one.
Where are you sending that? Is there a chat in here?
What?
Where are you sending?
Oh, I didn't send it. I was just telling you. I could try and send it.
I don't know if you thought you were going to change my mind from reading that NASA has general relativity simulators.
I don't think that anything I send is going to change your mind. That's not the point. But
Wow.
Is there a chat?
If you could offer me proof of the globe, like that would definitely change my mind.
Oh, we've already had proof of the globe. I don't think that's going to change your mind. Oh, there we go. Chat message. Send. There we go.
I asked for a computer program that could predict eclipses.
So again, computer programs are just taking the equations and making them into a visualization.
I know exactly what they are. Like I said, I'm a computer science engineer. My question is, why can't we build a model with our understanding of relativity and gravity that can predict eclipses based on the location of the moon, the earth, and the sun?
We can. That's what the equations do, and we can just make the equations into a visual model and we have programs.
So why does every single eclipse predictor in the universe use a 5,000-year-old book instead of one of these models that can be done with more accuracy? Could you prove that any don't? Like, that's what I've been looking for years, man.
Yes, those equations are the things that makes the prediction. So literally anyone can just build a computer and do that. It just takes more work. So when you're making like a computer model program or doing it to educate,
more work than going around the world collecting eclipse data from ancient civilizations.
No, work is in more computer processing power. So if you're doing a computer processing thing, you usually want to use the simplest equation to get the closest result. It doesn't have to be exact. Use F equals MA is fine as long as you get a close enough result. If you want to actually calculate pi to the 10 billionth digit or whatever, it's going to take a really powerful computer to do it. So in a computer program, the way computer programs work is you want to make them simple and use the least processing power possible, which means they don't use the most accurate, complicated scientific programs ever to do it. They just make a general thing to educate random people because you don't need a perfect model. Can you do it? Yes. You could build a model that does general relativity exactly. It's just going to take a shit ton of computer power that your home computer isn't going to be able to do unless you have a really good one.
Okay. But nobody's ever done it, was all my claim was. And I don't think they can, but I guess maybe a
No, they have done it.
mathematician could give it a shot.
Supercomputers do
But
that kind of stuff all the time.
they,
They do this modeling all
so
the time.
I'm asking for a program. I've been looking through this stuff for ages, man.
Go look at the research done in the field. It's saying
That's what I've been doing. You can't just say go do it when you've not done it.
No, I have done it. Like, this is really simple stuff. Like, everyone in science
Then
already
you can
knows
pull
this.
it up. If it was this simple, like if anything I'm saying, I can give you sources.
I don't know why you keep
that.
asking for a computer program, because a computer program is just the math put into a computer. If we have the math and the math works and we can demonstrate it without a computer, we can do it in a computer too, necessarily. Like, if I can do it without a computer, I can do it with a computer.
But my point is the math doesn't work.
Well, the math makes the predictions, which work as demonstrated in the site I gave you. That was the point of the site I gave you. Is that demonstrates the math works 100%, and then we can put that into a model if we want.
How does this demonstrate the math works?
It makes novel testable predictions which were never made before, which confirm that theory is right and that other theories no one else could do it. Novel testable predictions, like that thing you said in your introduction. That's how.
Sure, but look at all the massive assumptions that this thing starts with.
The assumptions don't matter. All that matters is, can it make testable predictions? If yes, it's
right.
What
testable prediction has it made?
The curvature of light around the sun, the eclipse data, the gravitational waves, the bending of light around universes, the amount of dark matter.
It hasn't done that. That's not what this is at all. This experiment.
The testing of the curvature of the light around the sun in the 1919 eclipse by Einstein is what showed was the original testable prediction made by general relativity. Like, that's literally what the site is showing. This was the first testable predictions, the first thing on the website. And there's more. There's other testable predictions on the website. You can just read them all.
So the prediction is that there would be a corona during a solar eclipse? This is insanity, right?
What? No.
What is the testable prediction?
The testable prediction was the exact amount of curvature of the light around the sun. That was the exact amount. So this was like not just
where is the exact amount shown?
When there's the big equation right in the middle.
Yeah, but they're saying that an amateur astronomer should be able to capture this phenomena with his own telescope and see. But this is absolutely untrue, because we can't verify that the exact curvature was correct. All we can verify that there was, in fact, a corona. And we know there's a corona because every full solar eclipse in the history of mankind has had a full solar corona. This isn't a novel testable prediction, Tom.
Taking photographs through a telescope is a significant level of difficulty and makes this very hard project for amateur astronomers who are not skilled with these techniques. So it's the opposite of what you said.
So they can do it.
The easiest method is to take a digital photograph of the star field and near the sun, so the photograph captures the stars as close to the solar limb as possible, but that also captures the image of the stars at least 3 to 4 times further from the center of the sun compared to solar radians. This distance, stars like Regulus.
So where do they show that their prediction was accurate? This is what's eluding me. I see that they say that they can make it, and I see that they say, oh, it happened. There was, in fact, a corona, but I don't see anything here that was a novel testable prediction.
That's all the big numbers right above that. It's predicting it with exact accuracy. So it's like saying it's not just there's going to be a corona.
They got it. How did they measure that they got it with that accuracy?
They wrote down the prediction of what it was going to be using the equations, and then they measured it and saw that the actual thing was correct within milliseconds.
Where does it say that?
Everywhere, like just literally right there.
Can you
in
highlight
that paragraph?
the text and send it to me? I don't see it.
The predictions, the measurement?
I want to see their prediction. I want to see their measurement.
By measuring how the images of the stars shift.
I see that they say they did it. I want to see their prediction and their measurement. I don't believe them.
Like Einstein's paper? You want Einstein's original paper that made the prediction?
No, I want a prediction that someone made using Einstein's math. I don't want Einstein's math again.
No, Einstein made the prediction. Einstein used the math.
Einstein made the prediction about the solar corona.
Yes, he made this prediction and measured it himself and published it in a paper. Yes. This was literally his prediction. Of the curvature of light around the sun, the starlight around the sun, that was his prediction, which he made and then confirmed with a
But you
telescope.
said the exact amount, and
Yep.
he confirmed that with a telescope. How would you confirm the exact amount of the curvature of the light around the moon with a telescope? Wouldn't you need a spectrograph?
Could be. Maybe he used that. I don't know. Like you can test the paper.
He used that 30 years before they invented.
No idea.
What
no
a
idea.
dude!
I know. This is how it works.
Dude.
So yes, he made the prediction.
Okay.
It was confirmed by him, and it's been
So
confirmed
I
by everyone
do
else.
vehemently deny that solar coronas are a prediction that was made by the theory of relativity, considering they were written down over 3,000 years ago.
Okay, it's not a solar corona. It's measuring the curvature of light from the stars behind the sun as it go around the sun to get to us.
And they're saying that we can see that by the
Yes.
phenomena of the solar corona, correct?
Through the solar corona. It's not.
Right. So the light in the solar corona, like which sends spectrographs like basically into real random number generators, because so much distortion gets blasted to them that everything we read is just like roll the dice, have some fun.
No.
Like it's
No. If it was a random number generator.
I know. Do you know what not a random number generator, a true random number generator that uses things that observe unpredictable phenomena to generate unpredictable numbers. Computers can't randomly generate numbers, Tom.
Right.
Don't
So if it was a random phenomenon, then it wouldn't follow a pattern. If it follows a pattern, we can predict it every single time, every single year with the exact same data for every single star as the sun passes by it and get it right every single time. Then it's not random.
If you could show me a paper that did that, that would blow my mind.
Einstein's paper. Original one.
No, he made the predictions. I want to see someone who tested them and showed he was right, bruh. I know he made the predictions.
No. He did it. He did the experiments, and so did everyone since. They keep doing it.
How?
How
did he measure?
You can do it like that. The paper I just sent you gave you how to measure it yourself. Can you
show me the part where it told me where I could measure it? I saw where it said I could do math.
It didn't where you said you could use a digital camera to measure the light around this. You can do it.
You can't use a digital camera to measure light. You use a digital camera to record a photograph of light.
Oh my God! What do you think measure light means?
A spectrograph. Give a numerical value for light, which is what a spectrograph does, not a camera.
All you need is to be able to see it and see where it is in relative to the sun. That's all you need to do. You can do it with the camera.
But that prediction hasn't changed since long before Einstein. He did not make a novel prediction.
No. That is wrong. This was Einstein's novel prediction. Newton made predictions similar to it for less gravitational bending of the light. He was wrong. Einstein was right. And before then, no one predicted that light would bend around the sun. They didn't know this. This is not something they knew millions of years. You couldn't even see it. They didn't have the ability to see it.
You couldn't see the solar corona billions of years ago?
You couldn't see the stars past them, well, thousands of years ago. That was the thing. You couldn't even see this back then, so no.
That's wild. I don't think we're going to get anywhere because I think spectrographs are just pure witchcraft. Like, they give different numbers every time. It's like a Ouija board, where you all hold the middle and then whatever you want to be true is true. Have you researched how the exoplanets were first discovered? Where the star wobble in 95, where these 4 drunk Swiss guys decided there was a planet, wrote the paper. It's absolute hilarity, man.
Well,
I would love to see predictions of where we can see what a spectrograph is going to say before a solar eclipse, and then record a spectrograph showing that. That would absolutely blow my mind. What we now constitute as a star wobble has completely made me lose all faith whatsoever in NASA spectrography. I absolutely think they're just silly men doing silly things.
I'm sure you think that, but they can build StarCraft and go to space, and you can't. So I think they're not very silly.
I would absolutely. I really hope we can do a part 2 just about the moon, because I would love to come prepared on that one. Here are all my positive claims you can tear up about the moon. Number 1, the footage and recordings from all Apollo 11 to 17 were obviously done on Earth. Number 2, Nixon communicated faster than the speed of light from the White House to the moon. Yeah, like how fast he responds to Neil Armstrong, too fast. The descent engine can't be heard in the landing speaker that Neil Armstrong's reading on Eagle when he's going down, despite it being like 19 inches from his head. Like, it should be the loudest noise in the background, but really he's going like, all right, 1,000 feet, 500 feet, 200 feet,
You mean
100
in
feet, going down.
space where there's
I
no
do.
sound?
Where there's 5 psi inside the LEM, by the way, not noves bound where there's vacuum.
Right,
but that does bring me on to my next point. Core tubes being hammered in Apollo 12 by Buzz Aldrin. You can hear them get hammered in. That's hilarious. I've watched all the footage. I know no human being has done that. It's insane, but I've watched all. There's no burn marks under the LEM, despite the descent engine being like one of the biggest engines of the time, or something like. I don't even remember. I'm gonna remember it not wrong. I think it's 46 kilonewtons squared. Orange juice in Apollo 15 spills over tons of the pictures during the EVA, the extravehicular, whatever it is. I forget the A. And orange juice can't spill in space because once you're below 1 psi, all liquids immediately boil in vacuum. And flexible pressurized suit would immediately become rigid in a vacuum. There's no way you could move cloth around with 7 psi inside.
Yeah, you can literally do that here on Earth. We have vacuum chambers. We can make vacuum chambers and show that the suits literally do still move even in a perfect vacuum.
I have only found one real video of an astronaut suit in a vacuum chamber, and it failed, and the water on his tongue started to boil, and they canceled. I forget his name, but it was from like 1965 before we went up.
Yeah, we can just go do it. Like you can literally pay to do it. You can do it.
I'm gonna build myself a vacuum chamber, and
I mean,
like
you can pay to go to a vacuum chamber that already exists. Go in a vacuum and do it yourself. You can literally rent the space and do it yourself.
That's pretty cool. That would blow my mind. Where's that?
I forget what the biggest one is. Like just Google biggest vacuum chamber. You can rent it. You can rent
the
it.
The biggest vacuum chamber is by NASA, and it's in my home state of Maryland, and it's got like 10 feet of concrete walls around it. You definitely can't go there.
Oh yeah, you can.
But there might be commercials.
Oh yeah, you
I've
can.
never seen it. No, another one in NASA. No way. I grew up outside of Goddard, man.
Yeah, you can get in. Yeah, you can. You can actually go there. You can actually message NASA and have them show you around the facility. They do that. That's cool.
They do show you around the facility. They don't let you in the vacuum chamber.
That's because it costs money. You got to rent it. You can do it. You can do experiments with it. Like they did it for YouTubers. YouTubers can go do it.
I would blow my mind.
What's his name? Brian something. There's many YouTube. There it is. Brian Cox visits the world's biggest vacuum chamber and drops a hammer and a feather at the same time for fun.
Brian Cox
visits the world's biggest vacuum
chamber. How cool! I will take a look at that. I wonder how real that is. How cool!
Oh, and also you can
he doesn't go inside it. It is the vacuum chamber I'm talking about.
Yeah,
but he does.
Yeah,
he uses a crane, my man. Oh, come on, he's not inside it. I told you.
Right. I mean, you could go inside it. He obviously.
There's no way they would let a civilian go inside their vacuum chamber in a suit, dude. Do you know how dangerous that is?
Yes.
There's no way.
That's how they test them.
I would love to see that. I don't think that they do. I don't think that 1/8 inch aluminum could contain 5 psi and 6.7 square cubic meters inside of a vacuum either. I definitely don't think that the LEM was even strong enough to be in a vacuum chamber.
It's definitely is. Like we see it in there all the time. That's what the.
Have you ever seen it?
Like the International Space Station is made of aluminum and steel and stuff, and it does it every day.
Have you ever seen it? The LEM?
The LEM, yes, like pictures of it. Actually, I think
no. Like, have you been to like the Air and Space Museum where they've got the training one and it was the extra or the spare or something in what is it, Dulles, Virginia?
I might have when I was a kid.
I've seen it a bunch. I grew up outside of DC, so it's wild.
Yeah.
I would like to build myself a vacuum chamber so that I could see that. It's certainly an interesting one. But if the Earth was a globe, well, then certainly no living beings could get through the Van Allen belt. So that ends the Apollo missions right there, in my opinion.
Why do you think that?
Because when radiation Heats up. Radiation kills us, my man. It's been a while since I've done my deep dives on the moon. It begins with a B. It's a certain effect that talks about when the non-ionized radiation goes through aluminum foil and becomes ionized, and becomes the deadly gamma radiation. But I can't remember the German physicist. It's Breistand or something
No,
super hard to
I
say.
know what the Van Allen belt is. I think. Why do you think no one can get past it?
I
Like,
think that the radiation would kill them.
why do you think
I
that?
thought
Like,
you were
it's
asking me why I
radiation.
thought radiation would kill people.
Long-term exposure to radiation kills people. Yes, you can be exposed to radiation for a short term and you're fine.
Why at the last minute did they pull the human test pilot from Orion and NASA? And why did the video, when they explained why they did it, say that we have not yet figured out how to get through the deadly Van Allen radiation belts?
That's dumb.
Okay.
Like there's several ways.
Good
One is that
defense.
you could go to the moon like when
When
it's behind the Earth, like in between when the Earth is in between the sun and the moon, and then you
what? The Van Allen radiation belts orbit the sun, or sorry, the Earth.
right.
In
So
three
so
different
the Earth
layers.
acts as a giant
They don't
shield, and so the radiation
go through.
hits the Van Allen belt and goes around it. And so if you're behind the Earth, you're protected. It doesn't like go back down.
You should look at some pictures of Van Allen belts. We should do a moon one, Tom. We should do a moon one. It'd be fun.
Right.
Or an ISS/moon one.
Wait. So the Van Allen belt is a gigantic magnetic shield that prevents like the radiation from hitting us, right? So,
Why were Van Allen's Geiger counters absolutely saturated for 28 days when he sent them up in Explorer 1 and Explorer 3?
probably because he sent them in front of the Earth instead of behind it. So
He sent them up in the North
if
Pole.
you have a shield, like if you have
That'd be behind
radiation shield in front of the shield, more radiation behind the shield, less radiation. Van Allen belt, big shield.
We should do a moon one. This is about the shape of the Earth. We should definitely do a moon one, a moon/ISS one, because I think I think you just haven't really looked at it too closely. It's not that hard to see. I'll back up all these positive claims.
How
in
NASA worked around Earth's radiation belt to land Apollo 11 on the moon.
I've read it all, man. I've even read when Alan Bean said, "Oh, we didn't even go that far," and then the guy's like, "What? They're 30,000 feet up." And he's like, "Well, I guess we went right through them." I read it all. Alan Bean's an astronaut.
Why does what he say relevant to the science? Like his words aren't science. Science is the science, the demonstrable, testable predictions. Not his words.
I agree. I just think they're funny, and I mean, this isn't the moon debate. This is the flat Earth debate. So I don't have all my sources ready on the moon. So I'm just going to make my positive claims, and if you invite me back for a Moon ISS one, I would love to come back for a Moon ISS talk. And I'm making all these positive claims about the ISS. No human beings have ever lived there or do live there now. There's definitely something that's shaped like the ISS that you can take a picture of in between the moon and the sun, but it can't be as big as they say the ISS is, and it can't be as far away as they say the ISS is, because the viewing location is too small for the math to work, and there's no way I would never be able to see it in Vietnam. Like, that's just annoying. It has to do. I can't ever. Like, I've tracked it on NASA's website. It never is viewable from my country. There are not many countries.
I don't know what countries you can see it from, but you can see it from Earth. Like, you can literally buy a telescope and see it.
I know you can even do it with a P900 camera, like the Nikon super zooms. You can definitely see it traverse. Definitely.
But then using the correct zoom, or knowing what the zoom is on your camera, you can calculate its exact size, speed, and distance.
You would need to make some assumptions.
Not really.
Well, if it traversed the sun, you would need to make an assumption of either the sun size, either the distance, or either the height. Just the angle wouldn't be enough for the math.
For the ISS, you don't have to discern anything about the sun. Like what?
If you were recording how long it took to traverse the sun, and you were using that to try to get an idea of how the size, sure.
No, you can just use the camera and knowing the magnification on the camera and looking at it move in reference to like.
Assuming you know how big it is, or you're assuming you know how far it is, but you'd need to know one of the two.
No, you just have a separate reference point. You just need to know how far the moon is away, and we can know how far the moon is away because we can. There's a little thing on it that the people who went there put a reflector where we can reflect.
We can't do that. NASA can.
Yeah, we could buy a laser. We could buy the laser and do it ourselves. It's definitely possible.
No, actually.
Yeah, it definitely is. I mean, you just need.
University tried to do it. Like I said, I'm not prepared for my moon debate, but university tried to do it, and the official answer that they arrived was that the ionosphere was blocking all of the laser back to their spectrographs, so that their observations were astronomically too close.
Okay.
Like I said, I'm not prepared for my moon debate. If you invite me back, I'd love to go into a moon debate. I really would. And I'd have all this evidence like. I know that the object that traverses the sun and the moon, the viewing angle is too small. I've already done the math for it to be consistent with the size and location. So there's like this little circle of where you can see it that traverses the land. And if they were being honest about the size and the distance, that little circle of where it would be visible, especially in front of the moon where there's light to block out, should be much bigger. But I don't have these sources ready to demonstrate because this is a flat Earth talk, not a moon one. And I've watched enough ISS live feeds that I've seen some crazy stuff. I've seen green screen failures. I've seen harness get tied up. I've seen dropped objects. I've seen them drop things that fall. The official NASA explanation is gravity pockets. It makes me laugh each time. The EVAs.
No gravity pockets. They literally just pushed it down. That's how. They didn't actually.
Yeah, I've seen a guy unscrewing a bolt and go boom. No, I'm not ready for my ISS.
When you're unscrewing a bolt, you have to put force on it, and you push with one finger more than the other, it goes down. I don't know if you're unscrewing a bolt, it doesn't come off straight; it falls because you put pressure on it.
It's how the bolt would go. But I'm not ready for my ISS debate. I've seen bubbles in the EVAs because I think they're all done in pools, right? But the best one is where people just like fade into the screen. Like opacity just goes up to 100 and they're just like, I'm here now. And objects do that as well, especially the microphones. I don't think the microphones are real. I think they're digital. I would love it if you invite me back and I can verify all these claims, but I'm not ready for that debate. And then the pictures of the Earth, like that's where I'm going with this, because this is about the flat Earth. This isn't just about leaving. I really started to look into the pictures of the Earth, and that's what everybody asks the flat earthers. And so you got to tell me which one. I've looked at them all. Saying that all of them are photoshopped is pretty dumb. A lot of the photographs that NASA gives are images that are created, right? And I think the Apollo 17 blue marble was probably a photograph of a model. And we know the one that was on iPhone, that one, we know that was created by Robert Simmons. That's not a conspiracy theory. Robert Simmons says, I created that for NASA because it's my job to teach.
Composite images are still images of the Earth, so that doesn't actually help your case.
Yes, but he's taking data, he's applying colors to data, and then he's wrapping that data around a 3D model of a ball. So it doesn't help us prove the shape of the Earth. Sure, it gives us information.
No, the images from NASA are usually just composite images, multiple images of the Earth put together, but they're all images of the Earth from space. So any one of them will work. They just wouldn't be as pretty.
I don't like. If you give me one, I'll analyze that one. But the iPhone one, he is a digital image creationist.
Earth from space. Image of the Earth from space. There you go. Got him. Unedited. Pictures from the Earth from space, unedited. Behold, NASA's first image of the whole Earth in decades.
Yeah, I've seen it. Send it through. I'll pull it up. It's a good one. So this is the one that I was talking about. This right here is the guy that made the one that was on the iPhone. He is a lead data visualizer and an information designer. My design is to make imagery from Earth sciences data. I turn data into pictures. If you listen to his interview, he really talks about wrapping it around a 3D model of a ball. Like, look how big
we can
the
make
US
models
is.
of the Earth too in computers, definitely. But here's a picture of the Earth that's just a picture from space, unedited.
The link I cut off. Let me copy it, see if it works. Gotcha. So that's an image of the sun or the satellite perfectly lined up with the sun at like noon in Mexico.
No, there's actually a little more shade on the right.
I suppose. How interesting.
I mean, obviously,
It's weird that it's a
they,
perfect circle, right? Like they say the Earth is an oblate spheroid, but that
it's not a
image is an
perfect circle.
absolute.
It's actually a little longer this
Really?
way. From the top and the bottom is longer than the right and the left. But obviously, they're not going to take the picture when the sun is behind the Earth because you wouldn't be able to see anything. It'd just be a giant ball of light.
No, it's a perfect circle.
No,
It's 496. I just outlined it on my screen. It's 496 by 496 pixels exactly.
So that's not how you measure a perfect circle. Like just the fact that it's the shape on your screen is not a representation of the shape of the Earth.
Of course not. The picture, the real live picture that was sent by NASA wouldn't be a real representation of the Earth.
No, it is. It's your screen. The pixels on your screen do not show the shape of the Earth accurately. It's like if
You're right.
draw,
The artist could have compressed it into a square. It's true.
No. Like it's literally an oblate spheroid. It is when you look
But
at
the picture isn't.
No, the picture is. You just can't see it clearly enough.
I see. That's why I used a tool on my screen to measure the pixels of the image.
Right, and that tool was just you. The pixels are not the same. Like I'm using one on mine. They're not. It's an oblate spheroid.
Oh, okay. Let me demonstrate it for chat. Tool wasn't just me. That would be a very inefficient way to do things. Sorry, because I only got a touchpad on this laptop. Control save. Perfect image.
Okay, so then now move it one pixel to the left and it would still be accurate. So you didn't make it perfectly to the size. You just guessed.
I could. You're right. I could throw that image into AutoCAD and
no. You could like literally just take what you just did and move it one pixel to the left, and it would still look perfectly. It's the same. So it's still an oblate spheroid.
So how much is it that it should be different?
Less than a pixel.
Less than a pixel.
Less than maybe a few pixels, but not much.
If the Earth is what? 12,000 diameter, and there are 500 pixels there, and the difference is about 200 miles at the equator of the pole. It'd be significantly more than a pixel.
No, it wouldn't. What? Because it's 200 miles around the circumference, which means given like just looking at the radius, it wouldn't be that much of a difference. It'd be like unnoticeable. Pretty hard to notice.
I will definitely fire that image into something where I can do more accurate. You're right. That was pretty quick and dirty, and I'll do the math right there. I'll take a look at that image. I've taken a look at many before. I'm guessing that I'll be able to find something like repeating clouds or the shape of, or sorry, the size of a continent will be wrong. They're usually pretty easy to debunk. I don't know that specific one. The ones that most people ask me about, so the ones that I've got prepared, are the Red Bull, which I love because you see him in there and the line's flat as can be. He jumps out into the horizon, and I mean, you probably obviously know this is a fisheye lens and it's not real, but the thought experiment I like to do, this is PowerPoint I did that circle with. I know that circle is an oblate spheroid, but just imagine how small the Earth would be if these really were the curve. And then, there's a part where it curves upside down. It curves upside down, and then he's about to get out, and it's flat again. The other one I get asked about is the U2 plane, and so I like to use the footage of Jamie from Mythbusters going up on the U2 plane. You can see here he's got the GoPro mounted. GoPro, we all know, have fisheye lenses. So I will give you my real problems. I'll post my real problems with that image you've given me. Right off, my initial thing is, why does it look like such a perfect circle? But here we can already see the curve starting at 5,000 feet. Then 10,000 feet, the curve is different on the right side than the left side. 50,000 feet, the curve's kind of there. But then
Okay,
the
how would you do it for not a picture, but actually like a YouTube video of like?
I have the YouTube video. I just don't really have a way to stream them. I can throw the link in chat. The link's right here.
You can just go to the page and share screen of the page.
True. I mean, that's completely.
So yeah, I'm just looking at one right here from the MiG plug. Name of the YouTube channel.
Yeah, I've seen those.
There's the curvature of the Earth, non-fisheye lens, just in space.
This would be the one.
Continuous footage from a plane.
No, share it. Let's see it. Or if you send me the link, I'll put it up.
I'm working on it. Damn it.
Yeah, I got it.
There you go.
It's weird that the atmosphere, or sorry, the horizon already has a curve, huh? I think that would wait till he gets high, huh? Oops.
What?
Now we'll watch it. It'll be fun.
Like it's on a hill.
Oh, look at that one. Not a curved lens at all. No, this is great footage. Definitely. Should we keep going, or?
Yeah, you could just literally look at the lens and see, even if you calculate the curvature, the Earth is still curved. Still curved.
Yeah, well, now it's curved down because he's tilting down. But what about what about here, where it curves upward? So we're in a bowl Earth now. Oh, come on, don't stop loading. That was going to be really funny. This is definitely a curved lens. It doesn't look as strong as a fisheye, but it's definitely a wide-angle lens, and that's definitely where the curve is coming from.
Sure, that's fine, but it wouldn't cause it to curve
for sure.
Both directions like that. That wouldn't work.
That's exactly how fisheye lenses work, as demonstrated.
No, you can like calculate the curvature of a fisheye lens to know how much curvature would apply to an image, and then know exactly that it's still curved.
Yeah, I know, I understand that, but you're missing a lot of unknown variables there. I mean, photography isn't quite that simple. Like when you're talking about a camera in motion, to say that you can just do the math on a lens and know exactly how much it's curving, it's kind of disingenuous, because you can get curves even on a pretty squared lens. If I take it straight up, you can demonstrate a curve there just based on shutter speed. So it's not really a genuine way to say that in a video. You're right. If I was on a tripod, I would have predictable curve all the time. But if I'm mounting it on the back of a MiG, not really. So here's a guy who's a great amateur balloonist. So I want to give him a shout out. And he's got some pictures that, I'll be honest with you, they aren't all totally straight. Not totally sure what it is, but they're way straighter than what we're normally fed. And they're pretty wild views. This is from, 75,000 feet? And this one right here is 110,000. And they've always been pretty wild to me. You've probably seen this video, because this is a flat Earth favorite. The dog cam sport, they make little pet cans, and they set this giant balloon up. And that one's one that always just blew me away, how straight that is all the way across. And even that hot spot under the sun on the clouds really just makes me look.
Looks curved to me.
There definitely is some curve there, and on their camera, as you see that balloon go, definitely. But at 120,000 feet, this isn't the same. This isn't the same pictures that were always being shown of the curvature of the Earth.
That looks the same to me. It looks like the same as all the other ones.
Interesting. Interesting.
Like all.
Well, you said an interesting thing at the beginning of this, that you said there's no way you could change my mind, which really kind of blew me away, Tom, because it's. There's definitely tons of ways people can change my mind, but like it's interesting that you would assume your opponent's mind can't be changed. It makes me think that your mind can't be changed. So like, isn't every picture you see going to have whatever curve you need it to?
No, I can make flat pictures real quick. It's easy, but the pictures aren't the evidence. It's like literally going.
No, I agree. I totally agree, and I'm just getting through the normal things that when people ask me pictures, like
Yeah, like I wouldn't say that.
this isn't.
I wouldn't say that like seeing a picture would convince me. Like it'd take a lot more than a picture. So the pictures wouldn't be like the greatest evidence unless you could actually go outside of the Earth. It could be a picture of the flat Earth in reference to the sun on a spaceship. That would be pretty good.
Yeah, I don't think you can. I don't think there's space, dude.
Yeah, I know, but I mean, that would
Right.
that would convince me. Like if we could go to space and like see pictures of the Earth, I'd be convinced by that.
Well, I mean, I guess if you launched your own rocket and it got up to like 100 miles where we think the firmament is and it exploded, right? Would that convince you something?
Yeah, like if I was on it for sure.
Yeah, but I wouldn't advise you to do that. Set up a camera first. So the satellites, I know you know all these answers. Like balloons can do most of them. NASA's one of the biggest helium consumers in North America. It's there's not really all that much obvious evidence in my mind that there are the satellites that we say. I did some math on some satellite TV here in Vietnam, and they definitely could still be pointing at towers. So I'm
What?
not. I know that's not much.
Pointing at towers. What?
Yeah, so I was looking at the angle and where they're going, and they could be pointing at a tower from a broadcast station in the
what's
city.
pointing at a tower?
Satellite TV. I'm sorry. I'm talking about satellite TV. I'm looking for demonstrable
Oh, you
evidence
mean
that
like the thing you
satellites
put on
orbit
your
the universe.
roof that you?
Sure, exactly. Exactly. Because I'm trying to figure out if satellites are exist. I'm trying to skip through these because it's a lot. And I'm saying that most of it can be done through underwater cables. I'm just trying to answer the normal answers here and looking at how NASA is one of the biggest importers of helium. GPS, right? Like that should be evidence of satellite.
NASA's one of the biggest importers of helium. Why is that important? Consumers? Yes, that makes sense.
Their balloon program is massive.
Balloon program. So
yeah.
What are they doing with all the balloons?
What do you mean? They're building them? They're using them? They're sending things up with the balloons?
Sure.
Like that satellite that Samsung went up and then landed on somebody's house, and was it?
Yeah, geoscience uses balloons all the time. Like what is this supposedly evidence of? Like the amount of helium required to put up stuff to equate to every single thing we have up there is just, there's not enough helium in the world to do that, but okay.
Sure, everything up there, but yeah, most of it I don't think is up there. I think GPS is ground-based.
Well, that's provably false, but okay. But the idea, even everything we can see up there, the amount of helium it would take to keep it up there is more than we have.
There probably have other ways. I haven't done the math on the helium, so if you're saying it's more helium than they're consuming per year, like I honestly just don't know. I haven't done the math.
I mean, helium isn't really like a popular thing. Like we don't really use it for much. So the fact that they're the biggest consumer of it, it really isn't like huge. It's not a big deal.
No, but if I believe that the world is flat, I've got to have some questions about satellites, right?
Sure.
So that's my only point. I'm not saying that I've proven all satellites are fake. I'm saying that a lot of things can be done by balloons that we assume are done by something in orbit. And I'm saying that a lot of things can be done by ground-based communication that we assume are done by orbit. Those are my only 2 points.
Yeah, you can always explain things in different ways. The evidence is which one makes testable predictions that can be confirmed. That's what evidence is. Just the fact that you can explain something isn't evidence of anything. Like everyone can explain anything in lots of different ways. So does the flat Earth model actually make any testable predictions?
I've got a few. We can skip to some experiments that I want to do. Specifically, I've done.
Could you tell me like what specifically? Do you have like a model? Do you think there's a ice wall? Is there an edge?
The ice wall seems to make sense to me. Obviously, the military is super interested in Antarctica. I don't see how the flat Earth can be true without there being a firmament or a dome over it. So that definitely makes some sense to me. But
that's a testable prediction. That would be a great testable prediction if we could like fly to the edge and see the ice wall or hit a wall. That would be great.
Great.
Yeah,
that would be great.
So, but you could.
We can't do that.
Well, we can actually. Like I actually looked up the cost to buy a ticket to Antarctica, and you can just go there. yourself?
Yeah, so it's like $7,000 for the cheapest cruise, and it's like 49,000 for the one that actually takes you to the South Pole. But you can't leave exactly where they tell you you're going to go. You're not allowed to roam around Antarctica. I'm not allowed to take an expedition crew to Antarctica. It violates the Antarctic Treaty, and any of the 70 countries could just throw a red flag. And even if I did get my permit that takes over $1 million to apply, I'm not allowed to bring animals to traverse, and I'm not allowed to bring fuel. So, like, there is no way with the Antarctic Treaty in place that I would legally be allowed to do it. If coronavirus is going to bring the world to an end and I can build myself a boat, you better believe it. I'm doing it, Tom. I swear to you, I'm going.
You could. You literally could. Like the Antarctic Treaty, no one's going to stop you. No one cares.
The U.S. military
will not stop you. I mean, I've already looked this up. You can just call them and go. Like, you just call them. Ticket. You can bring a car. You can bring fuel. You can do whatever you want. Like, not even an issue.
That would blow. Then I'll do it. Like, if you tell me the number, I guess if I just have to call them.
To Antarctica.
But yeah, here's some testable predictions that I've got and things that I want to observe and other experience I want to do. I'm a little locked down because I can't really travel, and the southern hemisphere is where a lot of my interest lies. So I've had this one idea that I've been toying around in my head for ages, where if I could find the equator perfectly and I could travel ideally in a perfect line west or east, in the flat earth model, I should start to veer southward. But in the globe earth model, I would completely stay on the exact same latitude. So the idea would be able to go somewhere perfectly on the equator and traverse maybe about 200 kilometers so that I could see if I've gone in the southern direction. The problems I don't really know how to answer yet are, how do I truly identify the equator? Should I use the sun, like go at the solstice in June? Should I use GPS, which I obviously, if I think the earth is flat, I've got some questions there. And then how would I determine my latitude at the end? So those are some questions I've got about there. Another idea that I've had, which I think would be easier to verify, would be going south in the southern hemisphere for long enough. On the globe model, you should get closer together.
Yeah.
On the flat earth, you should get farther apart, right?
Yep.
Like that should be something that's pretty easily to verify, minus corona. So this is one that I'm really thinking in my head. If I can go to Indonesia, which I've got some friends there, but maybe that one's not far south enough for the math to be simple because it might be too minor. Maybe I have to go farther into the hemisphere.
Yeah, just have somebody from America and somebody from Vietnam, and you could both go north or something.
How would we measure our distance if we did it that far apart? I was thinking we would need to use radio signals between us to measure distance. So if we're like totally across the world, obviously I don't trust GPS, right? Because I think GPS is
I don't think we would need to measure distance. I think we would just need to measure direction. If we can say we would both go north or both go south, either way, and we agree on north and south, we'll eventually meet. And I think that's going to be pretty good evidence.
Well, north, I mean, like in the flat earth model, you would be able to meet north. We'd both meet at North Pole. So it'd have to be south. But once again, the idea feasibly for the experiment wouldn't be us try to go all the way to the very middle of the South Pole where no human being minus military has ever seen. It would be easier
you don't need to go to the South Pole. What you need to do is just, assuming the world is round or whatever, and say if we go south, which like a little bit towards each other, we'll meet at this point. You can know, like, if the world is we'll know where we will meet.
I see what you're saying. So actually reverse the math from where the end point is and then start to walk from your starting point so that you'll meet at the same point, as opposed to constantly monitoring your data all the way through.
Yeah, you can just make a calculation and say if the world is round and we go at this way south, and we go south plus or minus 15 degrees or whatever, we'll meet exactly at this location.
Yeah, that's perfect. That's great. So what I would need to look in there to finalize that experiment, which is one of the foremost on my head. I hadn't thought of that one before the virus hit. So now I can't travel. I can't go south. I can't go southern hemisphere.
Is Vietnam shut down for the virus?
I couldn't get back in. So our lockdown's actually pretty easy, and I could leave my home and go away, but they would never let me come back as an American.
Gotcha.
That would be the only reason. But I like what you're talking about, designing it reverse from the ending point. I think that's something that's great. Another thing that I think, because flat earthers believe that if the sun's going over a flat plane, and the only reason that it doesn't change size as the perspective change would need to be like a lensatic manipulation of the atmosphere.
What doesn't
So
change size?
the sun through the day stays pretty much the same size all the way through the day.
Why wouldn't it?
Well, if you think about no atmosphere and you think about a flat Earth model, as the sun set and got farther in the flat Earth model,
flat Earth model,
smaller.
In the flat Earth model, I see why. Yeah, it would change size. Gotcha.
Yeah, it would need to. So the reason that it should be atmospheric conditions. So one thing that I'm thinking about is if I get a solar filter on my P900, I should be able to take pictures of the sun on near identical days, maybe one day apart, at greatly different altitudes. In the flat Earth model, I think that the sun should get smaller as I go higher. And I think the moon should as well, actually.
Yeah, that'll be interesting.
So that's one that I want to do. So I've outlined how I could do this in Vietnam. I don't think I can do it from a plane because I don't think that a plane would be stable enough. So I think mountain is my best bet. The tallest mountain in Vietnam is 3,000 meters. So I don't know what this is going to be, but this is something that I plan to do once the rainy season ends. Something I'm really looking forward to, going up there, taking pictures.
Well, here's a test for you. What do you think, based on your calculations, what would the difference be between the tallest mountain in Vietnam versus Everest or K2? And you could test going to both and seeing if the difference matches your calculations.
There's a lot that I still don't understand to make that prediction yet. I definitely would like to be able to make that prediction. And there's more that I need to study from that. So all the photography I have of the moon of the sun right now is from other people because I don't have a solar filter. I'll be getting that pretty soon though. So some people are telling me the sun does actually change during the day very slightly. And some people are saying that it doesn't. I want to get my own solar filter and test that myself. And it's so negligible that there's so many questions I have about, could it be atmospheric distortion? There's so many unknowns about that one that I want to get my own photography on there. So I think I need to learn a lot about solar photography before I can make that prediction.
Yeah. And there's a question. Josh Wayner asks, can Josh explain ground-based GPS technology? How would that triangulate and give us altitude?
The altitude is something I'm not so sure. That's a really good point. Okay. Now, the altitude for GPS I know is pretty notoriously wrong. At least the one on my phone is. And planes have altimeters. They don't really rely on GPS for altitude. So I haven't really given a serious consideration just in the triangulation of the location. Remember that
I think you meant like latitude or longitude.
Oh, okay. Then I would just talk about how Wilbur Voliv sent a radio signal all the way across the Atlantic before the discovery of the ionosphere. So if the Earth is flat, a relatively small tower can communicate signal very, very, very far if the Earth is flat. The altitude, I wouldn't know how they triangulate that, but all I'd need is 3 towers that can hit your location. I used to work search and rescue for the auxiliary of the United States Air Force called Civil Air Patrol, and we used to do triangulation on the emergency locator boxes inside aircraft. And all we would need to do is put our antenna on our roof in 3 points, 2 if we were lucky. But once we got 3 points, we could draw it on the map and know exactly where that ELT beacon was coming from. So it's really not hard to triangulate based on land base, and I've done it countless times.
Okay.
This was one that you were talking about that in one of your debates that really got me thinking. But then when I started to do research, because I remember from elementary school, we were taught that as you get farther away from the Earth, you should weigh less. And so I started trying to look in for what that formula was, and that was way more difficult than I expected that to be. I've only spent a couple of weeks looking on this one, so I'm certainly not finalized, but it would be a weird phenomena for an explanation to in the flat Earth if weight greatly changes at altitude. So I was wondering how I could observe that and how much or how high I would need to go to. So I found this guy, Ray Claiborne, who I have no reason to suspect he knows anything at all, who said that at 10,000 feet, it should be 150 pounds to 149.92. That's not all that hard to weigh. I could measure that just going up a mountain.
Yeah, they actually.
So I'm interested.
They do those experiments on YouTube. There's a bunch of those you could just copy and test to see if they're right.
Oh, that would be great. I didn't even think to search YouTube for that one yet. I was looking for a mathematical formula and found nothing.
Oh, and there's also another question for you, Joshua. Why do you believe the government that the pandemic is real? Do you believe in the
I believe I'm not allowed back in the country.
No, I think he's asking, like, do you believe, because there's a lot in America, there's a lot of people who think it's a conspiracy by the government and that COVID's not real.
I think it's definitely exaggerated by states that are trying to make Trump look bad. I think that they're doing PCR tests and they're finding people with coronaviruses. So, but that could be the flu and the cold. I don't know. I looked at the total death numbers from the CDC as of July 31st, and 1.58 million people had died. If you divide that by 7 and multiply it by 12, it's 2.6 million are targeted to die all through 2020. And in 2018, 2.8 million people died. So it doesn't seem to be worse than a bad flu season of total deaths in America. And it really blows my mind that I'm living in Saigon, Vietnam, where we had daily flights from Wuhan up until the end of March. And like we had nothing. We had less than 300 cases up until 2 weeks ago. And now a city in Vietnam is going through it again. So I've got a lot of questions and I don't have much that I know about that. Just a lot of confusion there, to be honest.
Okay.
What do you think about it?
I think it's definitely a thing. I think the numbers are real. It's the risk is not the death rate, but the hospitalization rate. The biggest problem with COVID is the fact that it's going to flood the hospitals. And then if the hospitals don't have beds, then people are going to die from every disease, not just COVID.
Right.
So the real issue isn't as much the death rate as it is the hospitalization rate, which is massive, significantly higher than the flu.
Yeah, I can understand that. And if it's really higher because COVID's way worse, then that's a real problem. If it's higher because everybody's super scared and acting a little hypochondriac or something, I don't really know. I was doing daily rides around the hospital district in Saigon back in like February and March to see if maybe the government was lying, keeping the numbers down, to see if they were really busy. And they were all super empty. And like I said, we had daily flights from Wuhan up until the end of March. So I think it's probably not as contagious as they're saying, even if it is having problems. So like I said, tons of questions there, tons of questions. And I agree with you, though, Tom, that we normally operate our hospitals and cities at like 98% capacity. Even the tiniest bad flu season can cause tons of unneeded deaths. And so another question I have, and this is math that I need to work out still, is there are tons of reports and all this flat Earth documentation about Polaris being visible below the southern parallel. So I understand there should be a little bit of refraction for a few degrees, but I'd like to get from someone who understands light refraction a little bit better than I do, their thoughts on what's the farthest south I would ever be able to see Polaris through the refraction and then go hunting for it somewhere. That's another experiment I'd really like to do.
Have you thought about like contacting the YouTuber like Globe Earther guys? Because they'll actually finance you and help you do it and go with you to do all these things. There's people on YouTube who would be willing to do this with you.
I have not. I'd be willing to do this with anyone, no matter what their theories are. Let's get some proof. Let's do some tests. You know?
Yeah, definitely. There's a bunch of YouTubers who are willing to actually do this and invest to try and help educate the flat earthers. So there are people who are willing to help on both sides. Willing to work.
That would be super cool. I would definitely be interested in anyone like that who wants to help design experiments, do experiments, and any of that. That's all about what I want to do. Because how else are we going to know if this is all just the biggest mind game of the 20th century? Like that was the end of my presentation. I skipped a bit, but it really was, will I be a flat earther forever? I'm not saying that my mind can't be changed at all. It's why I'm still designing experiments and doing these things. Like I believe that the earth was a globe up until 2 years ago. How could I possibly assume that I'm certain beyond reasonable doubt in 2 years that it's not. You know what I mean? And there's one more thing I want to real quick pull up. Because this is some things that I have been doing myself, going down. So I've done a lot, the flat earths do long distance tests all the time. And so this is the best that I've done so far. It's not so great. Honestly, the flat earthers on YouTube have better ones with laser tests, like an inch off the water at 20 miles. This one's only like 10.4 miles or 10.09 miles. There's the building that I can see. It's a wedding reception hall across the beach. And there's me counting all 7 stories. And then probably there's the beginning of that reception area. And then I am on the ocean, so I've probably got an average of 2 to 3 foot waves between me and that distance over the 10 miles. And I've done my own math to verify this calculator. I've even taken the time to draw it in AutoCAD to make sure that I'm right here. I was assuming a perfect sphere in AutoCAD, to be fair. But there definitely is this constant phenomena that we see too far, and that really does bug me. I've got my P900, and I see things that are way too far away constantly. And I've gone up multiple times in aircraft since I've been toying with this flat Earth theory. Once to the Philippines, once to Indonesia, and I remember sitting out there on my way to the Philippines, and I could see Manila already. I could see Indonesia, and I could still see Vietnam. And I know that there should be hundreds of miles of curvature, even at 30,000 feet, and I should be missing that. Like, I was seeing over 500 miles.
I sent you I put a link in the video of Vsauce actually explaining the curvature of light around bodies of water. I'd like for you to take a look at that. I also got a question for you. How does Josh explain maps made before the 1800s that demonstrate the Earth is round, since they could not make accurate maps without latitude at the time?
I can only think of globes made before 1800 that were round. I can't think of any maps that were made before 1800 that were round. I can think of a couple that were certainly laid out in the AE, and I can think of tons that are super sectional. I can't think of any map that any naval captain, or there were no pilots. Oh, there were airship pilots in the 1800s, so I guess I can't think of any map that any airship pilot or naval captain would use that was a sphere. That would really blow me away if I could see that.
I think they were modeled that the world was a sphere, and they used that to calculate direction that they were going in. That was kind of the point.
I think that the Navy captains have been using the exact same thing to calculate their charts forever, and I think they've all been flat maps. Oh, I think my presentation PC just died.
Oh, run out of batteries?
Yeah, I didn't plug in my laptop.
Oh, that's too bad. Well, yeah, I sent you a video from...
What's this? Oh, yeah, this is explaining how light curves around water.
Well, it's specifically about just moving kinds of illusions, and one of the things it addresses is how light goes around water, and it uses the Titanic example of why they couldn't see the iceberg until it was too late, and why the other ship didn't see them until it was too late. So it gives an explanation of the way cold air and warm air can diffuse light to cause the curvature of light around large bodies of water, which is what explains many of the different flat Earth tests over large bodies of water, why it looks flatter than it is, because of the temperature of the air and the currents.
Totally agree with that. I've been studying mirages only for about 3 or 4 months because I just got my camera. Actually, my family bought me the P900 to shut me up about this flat Earth nonsense, right?
Oh, that's like the flat Earth camera of choice, right?
Yeah, exactly. So and I've definitely demonstrated that quite a bit, and I'm still learning that. So I bet that video will be really helpful because I'm taking constant measurements of the air. And since it's Vietnam, the temperature here is super predictable. It's nice being on the equator. Like it's either raining or not, but besides that, the morning comes in the same every day, heats up the air the same day. So my understanding is that in order to raise an image, you would need colder air under warmer air, which I haven't yet seen in that Vung Tau Bay that I took a picture of.
What? No, it would be the temperature of the air would be the temperature the light is going through. So it wouldn't need to be above. It would be like it would go from an area of cold air to hot air, and that would reflect the light, or it would go from an area of hot air to cold air.
Yeah, exactly. I understand what you mean, and I'm not really an expert there. I'm definitely starting to study that because I need to understand. But I mean, everything on YouTube, it's not exactly trustworthy. There's something about being able to sit there and take your own pictures and observe things for yourself. And
yeah.
I've seen manipulated videos on the flat Earth side and the globe Earth side, and I'm not really big on taking other people's words for it on anything,
Oh, and by the way, I found you can do the expedition. Like there's a guy, Colin O'Brady, did one in 2018, an expedition of Antarctica, a 54-day journey where he just crossed the whole thing. And I'm looking at
Colin O'Brady.
Forbes right now. Flat Earth supporters now plan an Antarctic expedition to the edge of the world.
I want to go.
Yes, definitely. So yeah, they're doing this. This is not illegal. You can definitely do this.
I will definitely look into Colin O'Brady. I've got a tab up on him. That's not a name I've heard before. I haven't heard anything about his expeditions. So
yeah, and check out the Flat Earth supporters now plan an Antarctic expedition to the edge of the world kind of thing. So you can definitely do it. Just follow the same pathway, same methodology.
Definitely will. I think that being in the southern hemisphere is where we've got to be if we're going to find out if any of this is true or nonsense.
Yeah, for sure. The testable predictions, because Flat Earth definitely makes testable predictions. It's going to say there's a giant ice wall and there's a dome. That's a testable prediction. Better than theism, so I'll give you that much.
The dome is a little bit hard if the Antarctic Treaty is true, right? If we really can't go.
Well, yeah,
but if we can go.
Yes, because the thing I sent you just gives you a bunch of ways you can get there and you can actually go. So yeah, if we couldn't go, it would be hard to test. But if we can actually go, we can test it. We can find out for sure.
Definitely. I will. Oh, he's even got a whole track of his expedition here.
Yep.
Does he actually circumnavigate? Oh no, he only tells me day 13.
Circumnavigate what? He's going across.
Does he go south in South America and come up south of New Zealand?
On Antarctica, I believe.
On that journey? That was my question.
I think so.
That would be wild because I have not heard of anyone who did that before. That's very cool. I see it here, but I'm not seeing where you do that. And you said there's flat earthers planning that. Did you send that link?
No, I'll get that one. It's just Forbes. You just Google Forbes flat earthers plan to an expedition in Antarctica. It should pop up.
Yeah, I do see it.
Got it.
Pre-corona times. I'm kind of surprised I haven't heard anyone about this. Or anyone talk about this yet. But so far what I've found is that everyone who claims to make the trip goes and stops by that silver ball, which is hundreds and hundreds of miles away and from the South Pole, and then goes back.
Oh yeah, because that's like the only thing there to visit. There's not really, there's lots of ice to look at. Most people are going to go for the one thing that's actually interesting to look at.
I mean, the way Admiral Byrd talks about it, it was a whole brand new frontier in the 50s. He talks about it as the last place left for true adventure. And then all of a sudden it locked down and we never went back because of penguins. Do you really believe that?
No, I think we didn't go back because it's just a giant ball of ice. There's like there's not anything to do there except scientific research into ice cores.
You don't think there's gold and silver and all the rocks and mountains there?
There definitely could be under the miles of ice.
Oh, you just think it's too expensive to deep
dive?
So what about Operation Deep Freeze? Why do you think we sent, like, what was it, 1 million tons of bread to bury in Antarctica?
I think that was private enterprise thing that people did because they're crazy, not because the government or any like institution actually funded it. But yeah, I think that the reason people don't do digging in Antarctica is because it's so expensive. Like to get a ticket to Antarctica, like you said, it was like I think it's $12,000 from what I looked at. But yeah, it can get up to like
To
60
actually get
grand.
into the ring, yeah.
So just to do that costs that much money. Whereas to buy a ticket to Africa, where there's tons of gold and stuff to mine, you can get one for like less than $1,000. So it's much cheaper to do it there, and much cheaper to ship it across the ocean in the warm weather than the cold weather. It takes less equipment, so it makes a lot more sense that you do the mining in those locations, and it'd be a lot cheaper than to try and actually dig it up in Antarctica.
That makes sense. I've just never known the U.S. government to be deterred by cost when it comes to stealing more things. That's the most amazing thing about it is we gave it and split it with 8 other nations. I was like, hold on, if this is real, we wouldn't have done that.
I think it makes sense because I don't think the government's going to spend a lot of money to actually do that, especially for gold, because the government isn't interested in mining rock resources because they're useless for the most part. They're mining, if it was oil, if there was oil in Antarctica, we would be there. We'd be like, the Republic would be like, we're going to conquer this land. This is going to be our land. Do some fracking in Antarctica.
That's what the flat earthers need to do. They need to fake some oil core samples from Antarctica, and they'll be popularized in the
how flat earthers can prove it. Just be oil samples. Oil was discovered in Antarctica. We got full trips. We got just paid vacation.
And all of them take it out.
Yep.
So if you were
for you, does Josh understand just how hostile Antarctica is? How pristine it is? Pristine, pretty?
I don't think pristine would be the adjective I'd use, but definitely I think it's the most hostile place on Earth. I'm a flat earther. I think the sun never goes there, right? I don't believe in the 24-hour sun in Antarctica.
Why? How is it light there?
Like the same light. So I think there's a firmament around. So I believe there could be a 24-hour day in the southern summer, but it would be like a coffee cup caustic where the light, basically whatever the firmament is made out of, would carry the light in a ring. The same way if you shined a light on a dome and it would carry itself around. So I don't think that you'd be able to.
Top? Okay. Yeah, I see what you mean.
I don't really know what the sun is, to be honest. But I could demonstrate it in a coffee cup where I can send the light all the way around the outside of the ring and shine a spot sight on one side and on the other side. So I don't even know if that happens because all the videos on YouTube of the 24-hour sun in Antarctica are just ridiculous. The sun's either CG or the clouds are the same at the beginning of the end, or the sun, like there's a pole, a street sign, and once the sun goes behind it, it's completely eclipsed. Like they're all got problems, and the one that the U.S. military gives out misses like 8 hours every day, and so I'm really confused.
Oh, I think it cut out. Connection interruption.
That I've seen that faked a bunch of times. I don't know if a video would do it. I think I'd need to be there to believe that one.
Yeah, for sure. I think that's perfectly reasonable. I think you can definitely test that too. That you should be able to test just by going to Antarctica. You shouldn't need to go to the center to be able to see that.
Yeah, I should just need to go on December 21st.
Yeah.
As long as I go on the winter solstice, I should be able to see that. Well, I've heard different things. It seems to me that the reigning globe theory is anywhere south of the 60th parallel, you should see a 24-hour sun on December 21st, right?
I have no idea. I haven't looked into it.
Oh, okay. They disagree about even that, so it gets frustrating. So you think all of the long distance sites things are totally just misunderstanding refraction, even the laser tests?
Yeah, lasers are light too, so lasers are also affected by refraction. But I think that most of the flat Earth ones, yeah, they're all just misunderstanding the math of the refraction.
But there should be a way to make an experiment, check the temperature through the medium that the light traverses, and rule out refraction, right? Like that should, if you're saying refraction is pulling it up, we should still be able to design an experiment that would at least account for that.
Yeah, definitely.
right?
You can just have ships along the way measure the temperature and just do the calculation that way.
Yeah, I don't think that would be very difficult either. Especially here in Vietnam, where I could get fishermen to help me. They wouldn't care. They just take some money, make some cash. And so if you measure the line consistently, you wouldn't even need to do that long. There was one video on YouTube of them doing it on a frozen lake, and that was the whole point, was they were supposed to measure the temperature, but then they didn't measure the temperature. And that one really irritated me. So if you were to design the ultimate experiment to shut the flat earthers up, what would you do apart from some of the ones that I've already named and been hammering out? Because honestly, that's really what I've been looking for. Is I'm reaching out to other people. I'm trying to find other people to help me make predictions, design experiments. How can we know this for all?
Well, I think the simplest way is the one I talked about earlier, where we just, if we imagine the world is round and we go south, like not perfectly south, but south towards each other, like a certain number of degrees, we should be able to make a prediction that if the world is round, we'll meet closer than if the world is flat. And so we should be able to know where we're going to meet and predict that way. And I think that's the best way to show that the world is definitely round. Other than like just taking you to space or going to Antarctica. Those are fun ones, but more expensive.
Yeah, definitely. Those are super expensive. That one's a lot more feasible. I don't have to go that far to get south of the equator once borders open up.
Yeah.
Anything else that you've been dying to say to a flat earther, that just test this, just measure this?
Oh, there's a lot of tests you could do. Like the one, I like the one with the pendulum, where you build a gigantic pendulum. You can place it on different places on the Earth. You can measure how far it spins off its axis. It doesn't just go straight back and forth. That one's a really good one. I like that one.
I looked into that one, and the YouTube experimentation that I saw made me believe that I was destined to failure on that, and the response that I would be told was it was always because of my joint. So the socket that you need that can freely rotate the pendulum apparently starts to get into the multi-thousands of dollars before they say that it can accurately test it. I was a little heartbroken when I realized the Foucault pendulum in the National History Museum in D.C. that I'd been seeing my whole life actually has a motor at the top to make it swing the right direction. They didn't bother to spend the money on the proper ball joint.
Another one would be the fact that Venus and Mars go in front of the sun. That's a pretty good one.
I've just started really to dive into those transits because that's not something that the ancient philosophers wrote about, and that's kind of where I started my journey going forward, because everything that the ancients could do, I can do. So, I haven't really gotten a clear understanding of where the prediction methods are for these traversals so that I can set up to see one. But yeah, I definitely want to see that. There's Venus and Mars, both should be predictable, I think.
Yeah, you should just be able to Google it and say, when will Venus and Mars go across the sun? It should be predicted by general relativity, by the way. You know exactly when it's going to happen.
I have gone into a dead end. I will keep looking on that because that's something I want to take a picture of. The photography is really important to me to get my own. And especially because the Venus transversal is how the globe theory currently came with 93 million miles to the sun, isn't it?
I think it's one of the ways to calculate. I don't think it's the original way to calculate. I think the
okay.
The speed of light is.
That was one of the verifications.
Yeah, one of the ways. Yeah. There's a website that has like 100 ways to show the world is round, it isn't flat, or something like that.
All those giant lists I've seen have been silly ones, like they're talking about Eratosthenes, and I'm like, or east and west circumnavigation proves that.
There's a specific galaxy that you can only see in the southern hemisphere, I think, and you can go to the northern hemisphere, and if the world is flat, you should be able to see it because it's a lot closer than the other things that are farther away that you can't see.
I see. That's interesting. That's a good one.
Let's see.
That's one of the reasons I was thinking Polaris would be a good one to check if I can see it south of the equator, because it's bright and it's always there.
Yeah, for sure. And this one's the same kind of a thing. See if I can find it. The Sagnac effect is another one where you can measure the rotation speed of the Earth. Like if we're on a flat disk and if it's spinning, then the rotation speed should be greater on the outside next to the South Pole than at the North Pole, where it'd be less. Whereas if it were on a sphere, it'll be the greatest at the equator and less at the North Pole and less at the South Pole.
But I think that the aether is spinning above the Earth. I don't think the Earth is rotating.
Oh, we can actually
Like
measure.
whatever.
We can measure the rotation of the Earth using the Sagnac effect. There's ways you can actually measure that we are definitely.
How can you measure that besides besides like a laser gyroscope that's going to show like 12 to 17 degrees per hour depending on where and when and who makes it?
There's several ways to measure it. I'd have to like go to the site again to read it, but it's one of the things
So
listed.
that's
Oh, here,
that's one that's really
Supernova 1987A is the one.
Supernova 1987A.
100 proofs the Earth is a globe. Don't take it on faith is the website.
I'll definitely check that out. Maybe I can add a few to my list.
I'll put that in the chat.
Taking a look at this now. So you're saying that the location means, or the brightness means that it should be able to be seen past the equator, but the obfuscation of the curvature blocks it?
Yep.
Oh, this is cool because if it's in the southern, it's a test that I can do without leaving Vietnam. And that's definitely my favorite kind of test right now.
Well, I mean, you'd have to test it in the south and in the north to show that.
True, but I can begin the observations. Right. Definitely true. Definitely. Yep. Oh, the Mescata.net 100 proofs. Cool. I'll definitely go through these. Awesome.
Cool.
Well, Tom, I really do appreciate your time. I think our 2 hours is over. It's been a really good conversation.
Yeah, actually, I really enjoyed talking to you. You're a lot more open-minded than the other flat earthers I've talked to. Like, oh God. Freaking Witsit gets it. Nathan Thompson. I actually met Nathan Thompson in person once. We talked in Texas. That was pretty fun.
Is he the same personality in person as he is on YouTube?
Yeah, he's the exact same the whole time.
I saw your name of the video was goading him out, asking him why he won't come on and debate you.
Yeah. I challenged him to a debate on Modern Day Debate, but James said he was too afraid to do it. No.
Oh man. Just putting that out there. James said that.
Yep.
That's great. Oh, that's funny. If you want to have me back on, I'd love to talk about the moon and the ISS because honestly, there's not even a flat Earth conversation if you don't start there. Because you're right. If we've been to space, this is all nonsense.
Yeah. I think the fact that we can see it up there is pretty good evidence. We can do measurements and calculations to get the size and accuracy to know it is. Like we just compare it to a plane. We can look at a plane that's going across the same essential distance, then calculate based off of the plane size and speed.
Yeah, it's definitely got to be higher than a normal plane. I don't know what it is, but I can show you the reasons why I don't think people are living in it.
All right. Well, yeah, it was great talking with you. I'm going to get some food. I'm getting pretty hungry.
Cool, man. Thank you. Have a wonderful evening, Tom.
You too. Talk to you later.